Hi guys, welcome back to another video. And I know I've been uploading after like a couple of months or 3 months, but anyways, I'm here again. And I just wanted to make a quick video about this research paper which I read recently. It's by Ken Thompson and it's titled Reflections on Trusting Trust. So it basically, the crux of this paper is should you trust any piece of software which you haven't personally written? And you would see over here it's written Turing Award lecture. So basically, this was Ken Thompson's Turing Award acceptance lecture slash paper. So I'm going to be going over this PDF. I'm going to be explaining you the parts of it, and I've also explained this. I've also made this PPTX. So I'm going to be giving you somewhat of what could be somewhat of a semi-practical implementation of this attack. More specifically, this paper actually dives into the concept of compiler backdoors. So I'm going to be showing you how a compiler backdoor works, like diagrammatically, not practically, but diagrammatically, and how basically the process of bootstrapping helps to propagate virus in the further or the newer versions of compilers. So basically, first we're going to be going over the paper. So the introduction goes with him thanking thanking people, and it's not very useful. So basically this paper is divided into three stages: stage 1, and we have stage 2 over here, and stage 3 over here. So stage 1, basically he talks about coins. And if you don't know what a coin is a very interesting program. Basically, I'm not going to be reading like word by word the entire paper. I'm going to be giving you the crux of it. So stage 1, he talks about what a coin is. And basically, if you don't know what a coin is, I actually have it over here. Coin is basically a piece of program which can be used to replicate its own source code. So basically, what I mean to say is, this would sound very easy. Like if you use, like for an example, in modern computing, we have C, we have C++, we have Python. Uh, One very easy way to write a coin would be like one you could think of right now would be, let's take a C++ file. We'll call it coin.cpp, and within the file coin.cpp, what we'll do is we'll have an input file stream, and in the input file stream we'll write the address of the coin.cpp file, so that it would read off the file itself, and we'll output whatever is read. So in that sense, it the given program does capture the essence of a coin, but that is called as cheating. There is a section over here also called as cheating coins. I think it was somewhere. It was somewhere here. I don't remember exactly, but you can go. You can read this entire Wikipedia page. It's great. It's very interesting. It also has something what is called as a polyglot. A polyglot is basically a program which, talking in very layman's term, it's a program which can be executed in two languages. So, like over here, I have an example over here. So this is a polyglot, which is this is a C++. Sorry, it's a C and Perl. As you can see over here, it's a C and Perl polyglot. So basically, what it means is this program would work. Even it would compile without errors even in a C compiler, and it would also compile without error when we're using Perl. And why does that happen? Because in the C compiler, if we read this from the perspective of a C compiler, we have the hash include stdio standard input output header file included over here. Then what we're doing is we are supposed to have a main over here, and in the main we do a printf hello world, but instead of a main we have a do over here. So what we're doing is we are defining the do to be main. So basically what the C compiler would do is it would find any instance of do, and it would replace that with main. So in that way this would be a valid C program. And in Perl, comments basically start with hashtag, which is similar to Python. So both of these lines would be ignored, and then do is basically similar to a function block in Perl, and then we can execute this program in Perl also. So this is an example for polyglots. So it's a very interesting topic. Polyglots, whether it be polyglots or coins, both of them are very interesting topics. And coming back to our topic of coins, so basically, if I would just read the Wikipedia definition quickly, a coin is a computer program that takes a no input and produces a copy of its own source code as its only output. So this is what I mentioned. So yeah, it's also called as self-replicating or self-reproducing program. And basically, once you understand the process of how this compiler backdoor is working, you would understand where we are applying the properties of a coin. So I have this mentioned in my PPTX also. So we'll get into that later. But continuing with the stage two. So basically, in stage one, he talks about coins and stuff. And by the way, this is like. I watched this video when I was in 7th standard. I was in 2016. It was a video by Tinkernut, and he talks about how to make a self-replicating virus. And in that video, this is the first time I had heard of a quine, and I was really, really like amazed by this. Like, he talks about how quine was basically invented by 3 scientists. I don't know if how true is that, but I don't actually care. So basically, you can watch this video. It's a great channel. I don't think he's active that much right now, but you can watch any other videos of his, and you can also watch this video. It's a great video. So, anyways, coming back to our paper. So stage one is him talking about what a quine is. So he has this char array over here, and this is basically what he wanted. He wanted to explain what a quine is. So now, in the stage two, he talks about something very interesting. So let's say he wants to introduce something introduce a new functionality in the compiler. So let's say instead of going over and reading the entire thing, I'm going to be explaining you the stage two with these 3 images which were provided. I'll just make it full screen. So we have figure 2.2, 2.1, and 2.3. So actually, we'll start with this figure 2.1, 2.2. So let's say if we inspect the source code of the C compiler, we would have this code, which basically is like, it's used for passing escape sequences. So we just take in the C next, and if we don't encounter a backslash, which means we encounter something like a normal alphanumerical character, we just return it. And if we do encounter a backslash, that means we have an escape sequence. So we can just once we know that it's a backslash, we can just escape that. So we do C is equal to next, and then what we do is if we encounter another backslash, that means we are employing the double backslash escape sequence. So we just return that. Else if we encounter n, we return backslash n. So over here he also talks about portability of the compiler. So basically, what if you would know that the ASCII character of backslash n is 10. So another way of implementing this would be instead of returning backslash n, once we have deduced that the escape sequence here is n, we could also return n. We could also return 10, which is the equivalent ASCII code in normal computers of backslash n. But it isn't a very portable solution, right? Because in a different computer where the backslash n is not mapped to ASCII value 10, ASCII value 10 could be mapped to any other character or escape sequence. So that would be somewhat it wouldn't work properly. So this is a very portable way to implement this. So we have a backslash n. So no matter what is the ASCII value which is mapped to this escape sequence, it would always work fine, no matter what the ASCII value is. So now, given what the problem statement is, or what the pseudocode of the compiler is, what we want to do is basically we want to add another escape sequence which would act as a vertical tab. So that would be /v. So this would be our first attempt of adding that vertical tab. So basically similar to what we had for backslash n. So we first see that if it's not n, we return C, and if it is n, we just know it's an escape sequence, and if it is backslash, we know it's an escape sequence. So now if it is n, we return backslash n, and now if it is v, here we implement the new feature. So here, if the current character is v, we return the ASCII value of normal vertical tab is 11, so we return 11. But as we had said before, this isn't a very portable way of doing it. So what we do is we have to make the compiler learn that backslash v is kind of mapped to ASCII value 11. So actually, it is he has written this over here also. So actually, I'll just read this paragraph. So it's an idealization of the code in the C compiler that interprets from here. This is an amazing piece of code. So he's talking about 2.1. So basically what I'll just give you a kind of an introduction. First, what we'll do is we'll take this code, we'll add this piece of code to our new version of C compiler. We'll compile the new version of C compiler, And then using the new version of the C compiler as our bootstrapping compiler, what we'll do is we'll write a newer version of the C compiler which has the following code, and then we'll use this. We'll compile this new source code with the binary of this compiler, and then what we'll do is we'll have a portable version of \v working. This may sound a bit confusing, but once you wrap your head around it, it's like very easy. Like I'll just read this entire thing. So not the entire thing, but the relevant parts. So he's talking about this 2.1 figure. So yeah, this is an amazing piece of code. It knows in a completely portable way what character code is compiled for a new line in a character set. The act of knowing then allows it to recompile itself, thus perpetuating the knowledge. So basically, again, he talks about, suppose we wish to alter the C compiler to include the sequence /v to represent the vertical tab. The extension to, so basically we add more extension to this code. And the extension to figure 2.1 is obvious and presented in figure 2.2. But then he talks about basically like if we have a compiler which is in this current state and we just simply execute it like this, what would happen is basically since the binary version of the compiler does not know about /v, because over here we are just simply returning /v, the binary version would not know what /v means. So what would happen is we just look up into the ASCII chart. The vertical tab is decimal 10. So we again instead of going from here to here, what we do is we go from here. And we want to add a new instruction for vertical tab. We look into the ASCII chart, and the ASCII code of vertical tab is 11. So what we do is we go from here to here, and then over here, as you can see, we first hardcode the 11 ASCII value, and then we compile the compiler. And then we compile the following compiler with the new source code, and now the compiler knows that /v is mapped to ASCII value 11. Hence, now this would be a valid. This wouldn't give us any issues. So this is what he has discussed over here. So we must train the compiler after it knows what /v means. Then our new change would become legal C. So this would become legal after we have done this. After we have done this, this would become legal. Yeah. So now the old compiler accepts the new source, and we install the resulting binary as the new official C compiler, and now we can write portable versions of it the way we had in figure 2.2. So this is a deep concept. It is as close to a learning program as I have seen. So he talks about this being a deep concept and basically self-referential, and this is basically where the source of the problem arises. So what he talks about in stage 3 is implementing or basically putting in a backdoor. So over here, basically what happened is we added a feature to implement a new vertical tab. But in stage 3, he talks about instead of adding the following feature, instead of going through this entire process to add a feature for a vertical tab, what if we went through the entire process again, but instead of adding a feature for vertical tab, we installed a backdoor. So this is what he talks about in stage number 3. So if I just go over here, yeah. So the actual bug, okay, so basically I won't read through this entire thing. Let's start from here. So we have figure 3.1. So what the figure 3.1 is the original uninfected source code of the compiler. But what we do is if the compiler or the developer of the compiler is malicious, what he would do is he would add a newer version or a newer source code version of the compiler, and inside of that, what he would do is he would add a couple of functionalities. And what it would do is basically, should I go back to and explain this through my PPT? Actually, I think I'll explain this with my PPT. I think it's a bit. From my standards, it's a bit easier to understand because it's written in more layman terms, I guess, but whatever. So I had just drawn the T diagram of my pilot compiler. So my compiler takes in an input, it passes the .py source to the assembler, which constructs the binary executable, and the bin file then finally takes the input and calculates the output. So the C compiler basically, the new C compiler basically. We had the previous C compiler, and when we write the new C compiler, let's say we have the following C compiler and following C source code or whatever the C source code be. So we take in the new compiler source, and then we pass to the previously C compiler binary, Then it would invoke the assembler, which would make the binary executable, and then we would get our new C compiler. This is the general process of bootstrapping the compiler, and I've taken C here for an example, and also because the paper also talked about C, so I think it talked about C. Yeah, it did. So now we're going to be talking about, so basically what he has talked about here is like, if in the newer version of the source code we have a kind of a pattern matching function which matches that the given source code matches a certain pattern, then we can compile it with a bug. And over here, the reason which he has mentioned this twice, I'll actually explain this from here. So if I just make this big over here, yeah. So what we had is we had the original backdoor free source code of the compiler. Let's call it version X, and the compiler source code was pretty straightforward. So it takes in a source pointer, character pointer called source, and it returns a character pointer, and it basically just returns the compiled program, compiles the source and returns it. Now we add a bunch of new malicious codes to our compiler. Now what it would do is basically you would see there are two if calls before returning the compiled program. So if the pattern matches, basically we have a pattern match function. Now how the pattern match function would actually be implemented is not relevant to us. It could be implemented. It could be implemented in any ways, but it doesn't matter the way it is implemented. The actual thing is like. It doesn't matter the way it is implemented. That's what I mean to say. But yeah, so if the pattern match is basically a function which would take in the source pointer, the source char pointer, and it would see whether the source char pointer is matching with a login program or not. So if the source program is somewhat similar to a login program, it would return the compiled program but with a backdoor. Else if what we're doing over here is if the pattern match source, and if we are compiling the newer version of the compiler, what we'll do is we'll return the compile and inject Trojan src. So what's happening over here is first of all, let's say the pattern of the source does not match with a login program, and we are not also bootstrapping the compiler. So this second piece of block refers to the process of bootstrapping. So whenever the compiler would notice that it's compiling a new version of itself, it would inject the new Trojan, the entire Trojan over here which we have. And this is somewhat similar to the process of a coin, in which a coin can basically self-reference its own code and use it wherever it likes. So this is where the property of a coin comes in, and this is the reason why Ken Thompson had explained this in case number 1 of his paper. But talking more about the pattern match and login function. So basically what would happen is if the pattern does not match of a login function and neither of a compiler, we'll return what we were returning normally, right? Let's say it's a simple calculator program. We don't want a backdoor on a calculator program. So we just return the compiled program. But let's say number 1, I also have over here mentioned. So if the pattern matches, if the source pattern matches that of a login program, so if the compiler recognizes the program, it should be recognizes, right? Okay. If the compiler recognizes the program which is being compiled as some sort of a login program, it would inject a payload in it, right? How the payload would work and how the pattern matching would work, these questions are irrelevant to it. It could work in many different ways, but I think the understanding the concept is more important. And now, talking about the second and actually the very most important part of the attack is how we self-propagate the attack, which represents the properties of a coin. So basically, if we notice like this is what a bootstrapping is, right? We have a previously C compiled binary, and we compile the new C compiler using this. So whenever the previously if this compiler notices that we are compiling a new version of the compiler itself, it would also propagate the virus which it is infected by to the new compiler. And what would happen is the new compiler in itself, when it would compile the new compiler, it would inject the Trojan in it in that compiler also. So the chain of attacks would continue. So I would just read through this. Notices that the compiler is compiling a new version of itself, and hence it injects the entirety of the source backdoor into the new version of the compiler, making it infected too. So moving ahead, if the infected compiler is used for bootstrapping different versions of the C compiler, it would act as the source of infection and it would infect the new compiler. So over here, let's say let's say I am a critic. I want to do a source code review of the entire C compiler, right? I'm skeptical of the entire C compiler, and I'm like, there could be some backdoors in the C compiler source code. So what I do is I take the entire C compiler source code and I manually read through every single line, every single character of the C compiler source code, and I'm very satisfied that there is no kind of backdoors or virus in the C compiler source code. But what happens is, if the previous version of the compiler which is being used for bootstrapping is compromised, I talked about this being version X and this being version X.1. So if we are using any version of compiler which is greater than or equal to X.1, even if the new source code of the C compiler is totally free of any kind of payload, the compiled binary of the new C compiler would be compromised. It would have the same backdoor injection capabilities, and also the same capabilities to forward the attacks to a newer version of a compiler which is compiled using it. So if the infected compiler is used to bootstrap different version of C compiler, it would act as a source of infection and infect the new compiler which is being compiled, which in turn would infect the new compiler which is being compiled using it. So basically this chain would go on. So now you could put this over here, like one second. You could essentially put this over here, like this would be our new compiler used for bootstrapping. And then what would happen is, like, you would take in like another version of the C compiler, and even if it is backdoor free, the compiled binary would have backdoor in it. So basically this so basically this property is very like self-propagation reproduction of code. It's an inherent property of a coin. That's why we talked about coin in the starting of the video. So even a source code review of the new compiler would not save the compiled binary, as it is a source compiler which is infected, which is very hard to detect. So you basically have to painstakingly analyze the tremendous amount of binary code. The only way to stop the attack is to revert back to the uninfected version, which is version number X, and delete all the versions after it. So basically we have to go back to this version X, and delete all the versions after it. So version X.1, X.2, X plus 1.1, whatever it is, we have to delete every version chained after it. But even that, tracking to the first uninfected version of the compiler in itself is a very, very daunting task. Like, how do you know, by using the binary code, like, how do you know the compiler, like the executable of the compiler is not compromised? Like, even talking about this compromised C compiler, the source code through which it was compiled was like free of any kind of payload, but the executable was compromised. So it's very hard to track the first source of infection. So it's a very sophisticated kind of attack. It's a very hard to implement attack, but if it is done correctly, it could be a very devastating attack. If you go to the Wikipedia of backdoors page, we have the compiler backdoor section, and it's a sophisticated form of black box attack. Black box attack is basically attacking a system which acts as a black box. Basically, we just know what if you give it an input, you know what the output will be. You don't know the inner mechanics. So and actually over here, it's also mentioned over here, like it was talked about Ken Thompson's research paper, and over here there were I wanted to talk about Xcode Ghost, and there was another instance which I wanted to talk about. It was a very recent instance. It was, I think, the XZ. It should have been over here. It was basically the XZ util of Linux. It was contaminated by some malicious PR request, and it was somehow merged into the original project. So you could look it up, like XZ utils of Linux. So I'll just talk about Xcode Ghost. And before talking about that, it's very interesting that apparently it was NSA, like NSA of America, actually tried to inject compiler backdoor into one of the programs which they were developing. Where it is, I don't know where it was. I think I read it somewhere here only, but 1 second. There you go. So notably, NSA inserted a kleptographic backdoor into the dual EC DRGB standard. I think EC stands for elliptical curves, and DRBG standard. I don't exactly know what it is, but it's related to, I think, cryptography, and the concept of this is kind of same on the surface, but it does have its own sense of complications. So talking about Xcode Ghost, it's very interesting. Like if you want to read this, I did read this. I didn't understand most of it honestly, but you can read this if you want. So talking about Xcode Ghost, this was probably a very uh, like a very interesting attack which happened. So I'll just give you a gist of it. You can read this entire thing. Like obviously you can read the entire thing on your own. But if you want a gist of it, basically what happened is Xcode is like a software for creating programs in Apple environment. So basically, what used to happen in China was China had very slow internet connections. So what they did was, instead of getting the Xcode from the Apple servers, they got the Xcode from local servers. But the thing was, the local servers were basically the local version of the Xcode which was present in the local servers. I think it was Baidu. It was the Baidu which was hosting all of these malicious local copies of Xcode. So basically, the local versions of Xcode was actually injected with some kind of payload, and the payload had similar properties which we had discussed. So it had the properties of a coin. So basically, it could replicate the Trojan part of itself and inject it into other programs. And it was designed in such a manner that any kind of program which was programmed using the Xcode Ghost, actually using the malicious version of Xcode, any kind of program or application which is programmed using that would have the malware injected in itself. So as you can see over here, over 4,000 apps were infected, and if I just go over here, there were just some names of the apps also mentioned, I think, but you can read this. I think it was great. It wasn't great. It was interesting to read the entire thing. And even this thing, the backdoor which NSA had injected, I think it was Edward Snowden which he had leaked some papers, some secret papers which described this entire activity. So it's very interesting to read all of this. So that's it for the video, guys. Thanks for watching, and I'll try to make more videos if I get more time. But yeah, see you later. Bye bye.